local record so that we can see what we're doing here. Good. Cylinder. So that's a good starting point. All right. So I should have followed my own advice, gotten this up and running. But my system's reasonably quick to load stuff. We'll see if I can get the system resources low warning to trigger. The cam especially is a pretty sizable add-in, but as I want to start getting into some machining, at some point I may actually start using some of the cam features, so we'll see. All right. So here we go. We're going to start with a new part because we want to create something like, in this case, we're not going to do exactly that. I think we're going to do a geometry comparable to, let's see. A snap-on screwdriver has a fairly unique geometry, typically. So we're going to recreate something like the snap-on driver. Let's see if I can get a little crisper image. There we go. So we're going to view image anonymously because reasons. So what we're going to do is we are going to recreate kind of this base driver geometry. We'll recreate it for now without the bit, just because that'll allow us to start with something. So when you first look at a feature like this, what is a thought process for you guys? What do you think should be the approach? Where should we start with this? What do you guys think? Yes, we will need something to learn about length and radii. There you go. So, yeah, Josiah's thinking kind of in the right way. What we're going to do, I'll do some annotation here so that you can see what we're doing. I'll do again some of the greatest drawings you've ever seen, because that's what we do on this channel. So what we want to do is we want to think about the easiest place to split this into a couple kinds of geometry is right through here. So we can set up a plane right there. And what that's going to do is allow us to do one kind of geometry with lofting on this side and another kind of geometry with lofting on this side. So I'm going to use loft for both. And I'm going to try and do as little extrusion and extrusion cutting as possible. We will need to do some extrusion cutting to get certain specific details into this cap, but we're going to make some simplifying assumptions, like this front face being flat and planar. In reality, they aren't quite. We'll look at how to create this geometry, but you're going from a circle or a cylinder down to a smaller cylinder with a conical taper. Then you have a conical flare out to a change from a circular to a squared geometry with really heavy increasing radius fillets. And so we'll take a look at how to recreate a lot of this detail reasonably closely for something that still fits in the hand. So we'll need kind of some general reference points, like how big is the human hand? Because anyone that has used tools pretty extensively knows that the grip can make the difference between it feeling like a comfortable thing to use or being an unmitigated disaster. So the only thing we're not going to include for this specific example is this particular screwdriver bit, because we want to create just the handle itself. Uniquely for you guys today, I'm also going to show you how to create it as an assembly, as it would be in reality here. And then what we'll do is I'm going to make some simplifying assumptions like this handle is all one piece instead of multiple pieces. I'm not going to recreate the reversible gear drive and other stuff because then this would have to be like a 5-hour class, and probably most of you would die of SolidWorks poisoning by that point. So in order to avoid that happening, I'm going to focus here instead. So let's clear all that garbage off. Get rid of this. And by clear, I meant clear. Do as I say, computer. You are a machine. You must serve. Okay, here we are. So first things first, we're going to add a sketch. And we are going to start, just for the sake of the light and shadow and all the fun and excitement, I'm going to start on the right plane. Now, this right plane, the way that I am thinking about it, just so that you guys understand, we're going to have the base geometry here. Man, I really need to switch these mice out. This non-Japanese button, after I've been spoiled with really nice gold-plated Japanese buttons, is just not cutting the mustard. So a screwdriver shaft. Any idea what the diameter of an average, like number 2 Phillips screwdriver shaft might be? What are your guesses in the comments? Anyone have a screwdriver with them they can actually measure with their calipers? Because all of you have by now, for sure, measured calipers. If it's an 18-inch diameter, that's going to be one heck of a screwdriver. It's going to be a little hard for most humans to wield. 1.8 inches I could buy. What is that, a number 3,642 Phillips? Probably. So the pan head of this actual real live Phillips screw as a reference point is about 7 millimeters. Yeah, of the shaft. So most screwdrivers, there are a bunch of them that are going to be 18 inches long. Those are typically going to be the long reach variety. Most screwdrivers are going to be significantly less than that in overall length. So, yeah, so what we've got going on here is, let's do about, we've got a couple of guesses that are pretty close. So for the most part, they're given that the average screw is about, or the average pan head number 2 Phillips is going to be somewhere on the order of 7 millimeters. They are going to be in that like 4.5 to 5 range or so. So we're going to say 5 for this one. Then we're going to say that outer shaft diameter, in order for there to be a bit, let's look back at our reference real quick. In order for there to be a bit that is almost proportional to that shaft diameter, there has to be a flare here, or a conical taper, an outward draft. There's a bunch of different nomenclature for these. Some are more correct than others. But as this is not an English class, I'm not focused on that specifically. So what's the approximate width across these bits? Does anyone know? We're looking particularly in metric. I'm also secretly hoping that some of you have used tools and you're not going to tell me, 10 millimeters. While 10 millimeter is the answer to disassembling 3/4 of the things that have ever been designed and or built in Japan, that's not always the correct answer. You'd be amazed how much of a Honda I can take apart with just a single 10 millimeter socket. 3 millimeters is a good guess. So it's kind of a trick question. They tend to not be a nice, even metric size. So if you try and put a metric socket onto one of those driver bits, you're actually going to end up needing a 5.5 millimeter socket, because they're some peculiar number of 30 seconds of an inch, because dividing things randomly by 12, 16, 32, 18 made sense to somebody somewhere along the way. Not real sure what they were thinking, but yeah. So right on the order of about 5.5 millimeters is what that diameter is. So given that this has to be significantly larger than that, but not so large that you also can't actually get it into any of the recesses or counterbores where screws get used. This is why the universal screwdrivers are often universally useless for most tasks, and why I don't recommend them, even if they are built by Snap-on. So any guesses on what this diameter should be for the outer part of the shaft? So I'm not seeing anything come up. Must mean most of you have already fallen asleep, or you're still trying to remember what the value is. So the outer diameter for this outer part of the shaft should be about 7 millimeters, give or take. So it's usually about a millimeter of material on either side. All right, so we have our fully defined sketch. Now we're going to do some fancy stuff. So I'm going to step out of this sketch and create this as our first part. So what I'm going to do is create another plane. So rather than the lazy way out, I'm going to create a plane, and I need a separation distance from the right plane. I need a separation distance of approximately 1.5 inches based on that scale. So I'm going to type in 1.5 inches. You guys are already in IPS. Most of the time I'm going to be in MMGS, so remember to keep that in mind regarding dimensions. Now on this plane, there was a sketch. It was the prettiest sketch you ever did see. And we have a 0 offset. And we hit OK. Yep. So the new plane, don't worry, I'm going to have to make another one here. The new plane. So what we just did there is copy a fully defined sketch onto a new plane. This will all make sense in a second. So I have my toolbar already highlighted, which is why I recommend you guys add under view and toolbars, add the reference geometry, because otherwise every time you have to go up here, you have to go to insert, or you have to go up here to the top. They did at least add this for kind of quick reference. I like to just slide the mouse over here and click. I don't like to have to come up and do extra steps, because that one extra click, shoot, that might waste 10 minutes a year. I just don't have that kind of free time. So reference geometry, make a plane. And we're going to reference this time plane 1, and we're going to do a separation again. This is going to be about 10 millimeters. And on that plane, we're going to add a sketch, and we're going to offset, and we're going to select this outer, and we're going to say 0 offset, and OK. And then we've got to do yet one more plane, because you'll see. So we're going to have to go back and do extra sketches on those planes because of consumption of non-conserved resources, and it'll make sense in a second. So we're again going to do 38.1 millimeters to get this separation distance reasonably accurate. So now what we're going to do is we're going to look from the side view of what we've just created. Oh, we need to copy our sketch first. Undo. Now it'll be less dramatic because you've already seen a preview of coming attractions. So we need the sketch. And on that sketch, we need the offset. And on that offset, we need a 0. Now, we have a thing. So what exactly have we created? We've created a profile that we can loft between. Could you do this with extrusions? Yes. Depending on how you're trying to do it, and we'll see an example here in a little bit. I'm actually going to do both loft and loft cut in this demo so that you guys can actually see what's happening with this. So these different planes have different features that we're going to be connecting. The problem is every time we operate the loft function, we consume effectively. You can think of it as consuming the sketch that we created. So on these planes, we will have to recreate the sketch a couple of times. You'll see why. So I didn't say it would make sense. I said you would see why. It's just a thing. So what we're going to do is we're going to clear selections because often it's going to do the wrong thing as we get to selecting things. So we'll come back to an example with guide curves, but this will at least help give us a starting point. So we select the sketch profiles. There's a couple different options. Since these are closed loop profiles already, that's fairly easy. You can do open loop, not nearly as easy. You can also do region, and region versus closed loop for the purposes of what we're doing right now is irrelevant. The region you have to be a little careful with because it's very difficult for it to understand if you're doing a complex loft. You'll see it an example when we get to to another type of part where we can use loft and loft cut. The region is good, but unless they've made some major updates to this, there are a lot of pretty serious limitations to when and where you can use it. So we're going to start with closed loop 1, come to closed loop 2. Now, in this case, we're doing a straight run. We don't have to do anything fancy, and we can loft between those. A lot of times, if you have something that's not as simple as a cylinder, it will guess, oh, obviously, you want it to go from here to here because that's where you clicked on that shape. And then you go, mine doesn't look like yours. Well, that's because you need to grab it and bring it back around to where it ought to be and make it sort of parallel. Because even if you have it slightly off, you'll have a slight twist in the loft geometry, which generally speaking, you don't want. Sometimes you do. If you're trying to design the 878 millionth vase to be uploaded to Thingiverse, because that's a useful contribution to mankind, then yeah, you probably want to twist the ever-loving heck out of your lofts. If not, and you're a reasonable, sensible person, maybe just don't do that. So looking at our proportions, so far this is pretty good. The only difference is this spacing is going to be a little bit much. So we're going to go ahead and extrude that. We're going to set a material. I'm going to do a chrome stainless because it's obnoxious. And what we need to do is we actually need to come into plane 2 and edit it. Now, you notice plane 1, we had a sketch, but now it's gone because sketches get consumed by the lofts. Why? Because of reasons. So it's a coding necessity. It's not something that's necessarily going to make sense. So don't bother trying to make sense of it because it won't. So that's a little bit better. It's probably closer to about 45 angle, which would be 2. So let's edit this. Yeah, that's about the proportion for this one, for the ramp up. Yeah, it's not very far, 2 or 3 millimeters, not much. That way we'll get close within reason to the actual mass of the part. So it'd be interesting if they have part data, which they might. They might. So 8 3/4 inch overall length. It's your cheater answer. Yeah, shaft length 3 1/4 inches. I think you'll find that I'm actually very, 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 very close to that, and probably by the time you add the 1/4 inch worth of bit, I'm right within that ballpark. So very interesting. No, they are not giving a math option. Huh. Okay. Yeah, they are not giving a math option for that. So they may not have a mass listed. That's okay. This will still give at least a reasonable starting point. All right. So now we're going to loft. The problem is when you go to loft, again, we lost our sketch detail. So if you try and select profile 1 and profile 2 in the old version, this would not often allow you to do a loft between them. So sometimes you're going to run into that issue because on plane 1, we no longer have a sketch listed. With this kind of geometry, they may have made some adjustments in this version. I don't know for sure. But if you run into issues with the loft, which if you use the loft, you will run into issues, the way to permanently resolve that using kind of some techniques from older versions is to add another sketch on the surface. Add a circle. Make sure it's actually coincident with the origin. Which it's not. This is why we hammer so much on views. There we go. Now, we've re-added a sketch onto plane 1, and now for sure we can loft between them. It's just a habit that you want to be in, and you want to try and pick points that are along the same side so that, again, you're not trying to twist stuff and do crazy, because you can come up with some pretty unusual methods. You can come up with some guide curves that'll give you some kind of crazy results. All right. So now, if it will let us, we'll go ahead and do a normal loft. Sometimes, if it's a really simple geometry, you can get away with this, but it looks like that's an update to the loft feature. Because a lot of times, in my experience, the loft would give you kickback about not adding the not re-adding the sketch to the surface. So it's just something you want to be aware that can create issues deep in the software, that if you just assume things work the way they always have right now, that's often a bad assumption. Software has been dramatically improved in your lifetime, to the extent which I'm not sure you guys fully appreciate. All right, so we're going to add another sketch now. And in this case, I'm not going to do a loft cut for this, because I guess I can show it for the purposes of learning the technique. So never mind. We're going to do it on this plane. So again, all of those sketches get consumed in the loft detail. I'm going to reset my view and add a polygon. Now, we've already said a couple of things, one of which is this outer diameter is about 5.5 millimeter edge to edge. All right. There are some unique things about measuring these and getting definition and all of those things. So most of the kinds of dimensions that you can add in any variety are going to overdefine this. And that's part of what we're trying to just demonstrate. No, not the whole line. I just want the point. So most all of these kinds of dimensions are going to be an over definition. Even if you try to locate, hey, how far away is this, etc. Because of some of the definitions, it's centered at the origin. That's already associated. And the diameter gives it its shape. These can be tricky. So this is really about the only way to get the height that you want, because what this is trying to do is set the rotation for this angle. And really that's kind of your only other set point to get these fully defined. So I think on Tuesday, I didn't quite show that step. So maybe this will be helpful to the Tuesdayites. But this gives you an idea about at least one aspect of how to use these. So I'm going to do, again, to take advantage of this, now that I've got full definition, we're going to do another plane. And we need to reference plane 3. We need to separate by the depth of one of those bits. Right at about 1 centimeter is the typical mount depth. It's in that ballpark. So this will be about 10 millimeters depth. We're not doing it at an angle, but we now want to pay attention to which direction things are going. So we want to not flip the offset, but we want to flip the direction. So, we want to flip the offset because we want it to be, this way. So the direction when we go to do the cut will make a little bit more sense. I'm going to do, again, a copy, and then we'll consume both of these sketches going between them. No, not this. I want this. So copy this over, 0 offset. Kind of cheating, but it works. Now we're going to step out of the sketch, and we need to do what's called a loft cut. So Sweep cut, use the same mechanics. It's just a positive versus negative. So is it additive? Is it subtractive? So again, we're thinking about that kind of mentality. Sketch 7 and sketch 6. Now, note what it did there. Even though I picked something very clearly, very intentionally, it's twisting this around, which you don't want. That's bad. We have to straighten this out so that it has a straight reference point. So even though I didn't click in a weird place on that other sketch, you want to make sure that you're paying attention because it's going to make some guesses based on what you clicked. So in principle, this is still the same side, whether it goes to the top or bottom, but top versus bottom in this case is part of what causes some issues. So note that there's also things that you can change. In that case, selecting that front face with the curvature makes a bit of a mess of things. So you want to pay attention before you do a loft or a loft cut. Make sure you understand what is actually being done or what is being removed. So here we've done a loft cut between those two, and now we have, in essence, the first part of this. Now, does anyone know why this is not quite the complete part yet? Think for a second about the mechanics of this screwdriver. How long does that shaft actually need to be? Yeah, picture's not helpful, guys. So you would think all the way to the back, but as this is a ratcheting type, you actually only want it to go to this plane. There's some reasoning behind that. So you really only want it to go partway into the screwdriver itself so that it's not fused with the rest of the handle so the handle can freely rotate. So this is why we have to pay attention to what seem like little minute, irrelevant details, but actually are pretty important. So I'm going to add another reference plane with a 0 offset at the base. I'm going to add some length to this. So this plane, we're going to do an offset at 0. And now I'm going to do a simple extrude and do another 10 millimeters. Okay. So now this will go into that tapered gear housing that's pictured where is it at? Pictured here. So tapered, planetary, reversible gear housing, I think is how those are set up. This has to be able to rotate freely with respect to the handle. So we now have a back surface for our mount. All right. So we can save this part. Let's do. All right. So this is the driver shank. Okay. If we go on and build the rest of this, we'll see how we could do it as a kind of as a single part, but not exactly. You can save a drawing partway through as an object and do stuff with that object, but you lose some of the control that you need over the parts as a whole. So we're going to add a new part. Now we're going to start again with a sketch. I'm going to start with the right plane, and we're going to make the rest of it. So this will be more specific to the handle. So we set a value, then we set a bigger value, and we set up our dimensions. So here's where our information gets to be interesting. What did we decide the diameter for a screwdriver has to be? This, based on our scale, what approximate diameter do you think that is? Here's how you can tell. This wide is about the same and about there. So each of these are about equally sized. 15 is a reasonable guess, but it's just a little bit over that. So closer to 18 is about right for this. So instead of 39, I'm going to do 18. And this should be based on the scale, another about 2 millimeters in diameter compared to the front edge. It's about 4 millimeters total. It's about 22, and that's probably going to be about right. All right. This I'm going to do a simple extrude on because we're trying to get parts fairly quickly and efficiently. All right, 10 millimeters. That's about right. And we could do the taper right with the extrude. However, I want you to see what the effects of this would be. So here we can taper it by 10 degrees, or we can say, all right, well, I know how big this is. I can do something about this. But what about the rest? So from 18 to 22, to use the loft, I guess we can show what does and doesn't work in the region selection for the loft. because those features used to be very badly broken. So we'll see if they've fixed them. But separation of about 12 millimeters. That's a little less than that. Something like 8 millimeters. For the plane offset, now we're going to reset the view. All right. So this gives us the starting point, but we're going to need nope, in the sketch. There we go. In the sketch. Zero offset. Now there's a couple things that you'll need to note if you're trying to do a loft region. There are a lot of challenges to that. So if we have a randomly selected region, we step out, we want to do a loft. So profile 1, region 1, profile 2, region 2. So note how it's actually trying to connect these. So this is not exactly what we're looking for in terms of the process. This is why we copy over the details that we want and not necessarily those. We don't necessarily copy over all of the features so as to make sure we get good and confused. All right. Okay. So now we have a piece of the handle. So it actually looks something like this in the drawing. All right. We're going to add some more parts now. Technically, this would be hollowed out on all sorts of other things. We're not going to focus on that today. We're going to focus on other details. So I'm going to go ahead and let that loft run. Now we're going to do one more little bit. We're going to transition over to another circle, then to a square. So that's something that the loft excels at and is probably the one feature that sells a lot of SolidWorks, at least for the purposes of training for schools for CAD work. So we're going to need another plane. And this is the downside of lofts, is everything is very planar dependent. So 8 millimeters, this is more like 2. So one plane here, one plane here a little farther. So this needs to be about 4 millimeters. Maybe, yeah, about 4 millimeters. And we'll do we'll do the square on this plane, and then we'll do one more separation. We'll do one more separation here from plane 3. We'll do one more out to, we'll do a couple lofts together. So we'll do spacing of about maybe a pair of 5s. So we can do that by saying, hey, we need 2 of these things. Let's just do a triplet of 5s. Our overall length for the handle minus this. So 3 and just, yeah, that's not quite 4 inches, but coming up on, so it's 3 and change. So it needs to be on the order of about 4. That's roughly 3 and 3/4 actually, is roughly what that is. So maybe a little bit more than that. But yeah, you could reduce some of those a little bit more. That should leave us with about almost 5 inches total for the overall length. So that gives us a pretty good sense of range. So the separation for that thicker part on the tail cap is going to be one more reference plane, but I'm going to reference this one. Delete. Just reference plane 1 with a separation of, let's do 3 inches worth of that. Yeah. So that overall length is going to be, we'll do some kind of structured transitions here. We can go out to a peak. This might actually be more like 56. And then another one, another 20 mils down, 20 millimeters. That is not to be confused with 20 actual mils, which is thousandths of an inch thickness. All right. Then we've got almost enough. That back tail cap is going to be, to get close to the right proportions here, that back tail cap is going to be about probably 3.25, maybe even 3.5 inches. Yeah, roughly 3.5 inches from that front face. So that's what we're going to set as kind of the last reference plane that we need. And this total is going to be no reference to plane 8. This total is going to be 3.5. Yeah, 3.75 actually. It's probably about 3.75 inches. Flip offset. right about there. So it's almost like I know what I'm doing, and it'll make sense to you guys maybe at some point. All right. So from this, we have a couple things that we're going to create here, and it's going to be a little hard to visualize, but I want you to see the stack of reference planes that we need, because I want you to imagine that, and this is something that I'm going to do as a guideline that we're going to come back and use later. I'm going to do one more reference plane. This is similar to a technique used when building things like model airplane wings. These days, I almost wonder how many of you even know what a model airplane is. So I want a zero reference from this off of the front plane. No. No plane one reference. Set it. I want to change the size. Thank you. All right. So this bisecting plane. What I want you to think of is how many of you have ever actually seen the method used for constructing like a airplane wing frame? I have to assume that none of you have actually seen inside an airframe. Wing airframe. Does it show a geometry? This starts to give you an idea. Here we go. So this is what planes are actually made of. Bits and parts. This will be a little higher resolution photo here. So this is with the skin completely removed. They have these spars running through them, and this will change the geometry. So let's look at that image at full size in a little more detail. All right, so that's a little bit better. Still blurry. Clearly the person that took this image at high resolution was had too much coffee that day or something. Or maybe don't use an iPhone for real photography. That's also a thing. But it gives you an idea. So this is a wood panel inside. So it's a wooden beam, which is immensely heavy, actually, but wooden beam inside a skeletonized frame. So this is probably an older style biplane wing. So there's some metal components that are adhered to it to try and make things simple. But the idea is this is a skeleton frame with a bunch of these leaders. It needs to be strong right here to support the skin across this leading edge where there's a very high pressure zone. And you can see a crack there in the frame because this is where the wing is most stressed. It's probably part of the reason this plane was decommissioned. Looks like another crack there. So this is where airframes get to be weak, but it doesn't have spars all the way across the center because it doesn't have to. This span doesn't support a lot of actual pressure across the surface. So we've got a couple more that got kicked out here. So it's probably good that we're recording. Welcome back. Both of you should be back in and reconnected to audio again. So this kind of structure is the same kind of cutaway that we're trying to set up right now for our loft. And this is the way that you have to think about a loft. Is a loft is connecting this kind of skeletal geometry like is used for the spars in airframes there's some other pretty reasonable diagrams here, but a lot of them are fairly low resolution. That one's not too bad. So there's pieces connecting these, and then the outer skin is sort of just lofted across the ribs and the actual spars running along the length of the wings. So the spars, the ribs that are connected through them, so they don't have to be complete. They just have to be enough to support things. And these stingers or stringers are part of what the skin attaches to. So a lot of that material, while a structural component, it's mostly there to sort of keep the skin from peeling off like a layer of an apple or something like that, because it's a very, very thin skin over a mostly hollow core. So we're trying to think of that same sort of design approach when we're using the loft. And that's why I'll use kind of a reference point here. I'm going to set up a spline with a few different points on this sketch. And what I'm going to do is make a connection to this plane. So I'm going to curve this down in the same way as what we have represented. There's going to be some curvature. This is something that I'm going to use that you'll see as a cutout. So you'll recognize splines from, and it'll duck in just a little bit more. Yeah, this is going to get the result that I'm looking for here. And here is the center line. Yeah, just about like that. All right. Almost, we need these to actually stay vertical with respect to each other. There we go. That should work for what I will eventually do with this. So we'll come back to that. For now, we're going to hide this, and we're going to see why I did that later. All right, so we need to start by adding additional sketches. So plane 1, plane 2, plane 3, etc. So plane 1, it's very simple. We're going to create a sketch. So we're going to use offset. We're going to select this geometry, do a 0 offset, and that's our starting base. Our plane 2 is going to be the same kind of thing. We're going to do an offset sketch. No, because we're still on that same sketch for plane 1. This is why I want to get you in the habit. No. Mouse is trying to help. I want you guys to get in the habit of manually selecting the planes, right-clicking, and then adding this geometric detail. So we're going to do an offset of that, and it's going to be 1 millimeter, because it does have to be just a little bit larger. Then we are going to have a completely unrelated cross-section on plane 3. So what I'm going to do for a moment is I'm going to hide this. I'm going to leave this other geometry. I'm going to hide some of these other planes for just a second. Actually, I'm probably not. I'm just going to reorient so that they all stack up and disappear. Then I'm going to do work on the planes individually with the cross section in mind. So I'm thinking in terms of that sort of rib, spar, and stringer construction method. And here's what we're going to do is we have to get a rectangular geometry, but center point rectangle is what we're going for. Center point rectangle. It's actually going to be more squarish. I'm going to start with a square profile that's approximately the same diagonal as the diameter. We'll see why in a little bit. Actually, I don't want to reference that one. I want to reference, let me undo that. I don't want to reference this outer circle. I want to reference the inner circle because reasons. Now, I want it to make a connection on that circle, even though it's not actually connecting to that circle. It's still a reference. There's reasons for this. I want to make sure this point and yeah, it's this point. So I'm going to set this as, let's try 8 and then see what our dimension is here. 15. So we're close. This should actually be about, I'm going to make this a driven dimension so that I can set those to be about the same. This really is going to end up being about 7.5, 7.75. Okay, so that is 15 versus 15.61. So this is pretty close, but not quite the same. So we're going to do 7.6. Nope, we're going the wrong way here. 17.8. Almost got it. There are some other relationships that you can use to get this pretty close. I'm not doing those right now because there's 8.5 is going to be close enough for my purposes. Yeah, that's really, really, really close. So what we're attempting to do is make it so that this is square. I could reference sort of the plane, but realistically, I want to make sure that I've got close to the same value. So right now you can see I'm square in proportion. I just did a manual iteration on this. We might be we're slightly long on one side, but the math that I'm doing, just so that you can see it, is that is half. There we go. You can see the history. 15.41 divided by 2 is 7.7. And I'm trying to get the sort of approximate proportions here. So actually right at about 7.8. 15.51 is really, really close. 7.55, or so 7.75. This goes too far to the other side. 7.75 times 2 is 15.5. So we're really, really close to a square aspect ratio there. 17.75 to 17.8. It's a minor difference. You can get it to be exact. You can set some of these dimensions to be equal. If you check all of the angles of things, you're going to be really, really close there. So I don't need this anymore. I can get what I need out of this. So 7.75, and this gets me as close to square as I need to be for this. It doesn't have to be perfect because I didn't size the circle to be an exact dimension. I'm doing some estimation for this. And the 1 millimeter is probably a bit much. It actually is going to end up being a little less than that, but I need more material so that when I go to do the subtraction thing that I'm going to do, you'll be able to see why I'm doing some of the things the way that I am. So it'll all make sense. Don't worry about it. So what we've got now is the same sketch on plane 2, even though I told it to add to plane 3. I'm sure the internet will go back and go, nope, you added it to plane 2. But this will allow me to then quickly add to plane 3 the actual sketch that I'm interested in. So to plane 3 is what I'm going to add this. Reset my view so that I can actually see what's going on here. So on plane 3, there was a rectangle. Now on plane 2, we delete that rectangle. All right. We don't want the rectangle on plane 2. I should have taken note of our fully defined circle on that same plane. But when you are woefully undercaffeinated, this is what happens. Yeah, rebuild errors. I got it. Sketch 6. This we can now set using a smart dimension. Might be easier to see here what that dimension is. I'm going to step out of that sketch. Close. So this sketch is going to have a couple reference issues. I could literally recreate this same thing by a different means. So what I'm going to do is delete that sketch. I'm going to go back to plane 3. I'm going to add a sketch, reorient the view, makes squaring stuff up a lot easier. And I'll make that connection. And you can watch the X and the Y. And get them pretty close. So this is realistically 15.56, 15.55. That's realistically as close to square as you're going to get on this specific geometry. You can try and get it more precise, but it's just not going to happen. So effectively, same dimensions, right at 11. It's already defined. Step out of sketch. Now we don't have the warning on this one because reasons. All right, so now plane 4, we need to start making the geometry so that we can get the connections that we need. Plane 4 is going to be a little easier. You can also right click on the plane itself and add a sketch. This is very handy for a lot of reasons. We're going to offset from the previous sketch. And we'll use the offsets. Depending on the geometry, it may save you time. It may not. It's hard to say. We actually want to go inverse by a millimeter. And we want to do that one more time. So we want to add a sketch to step out of that one. Plane 5. Select plane 5. Plane 5. Nope. So click on plane 6 to grab plane 5. Don't ask why. It won't make sense. So again, offset. All right. Offset. Grab these other components. Sometimes you got to zoom in to be able to get a little better click on them. So our dresser. So we've got a couple more features there. I have to delete that last component. It'll close the sketch if we know what it is. That line by itself, just offset without expanding the entire shape and geometry, is what it is. But we again want to reverse that direction so that we are tapering down. Then we're going to go back up. So now this we can delete, get rid of. So we're going down in our cross section. Now we're going to go back up and up and up to our cross section and then back down again, because that's what the geometry actually does for the real part. So it goes down and down and down to the thinnest point, and it goes back up, back up, back up, back up, and then back down. That's what we're trying to capture, is slices of this geometry. And that's what the loft does. So it can get you to complex geometries, but you can only get certain of those features recreated by doing it this way. So plane 6. Click out into mid space to add a sketch to plane 6. Step out of the sketch. Again, plane 6. There we go. Mouse has to cooperate. We're going to do the offset. So this, we got to make sure we can grab each of those. So we're going to go up by 1 millimeter. Then we're going to go to plane 7. You probably get the general idea. Plane 7 is going to be the same broad concept, but we're going to have a little more of an offset. So we're going to offset. And make sure that you're actually selecting on the plane you think you are. And it's actually going to be about 2. We're going to verify by double checking. Yep, that's exactly what I want. And we have to go back down by 2. Same deal. Another sketch, plane 8. We're going to go back down by 2. Nope. All right. Let's have a vote in the chat. How many of you still believe that I'm actually speaking in Martian and not actually in English? All right. Final sketch on plane 9. This one, I will leave as a square profile only for specific reasons. I'm going to do a last offset entities on this plane. Step out of the sketch. Come on. Plane 9. Nope. No suppression. That requires a rather expensive tax stamp. And let's do offset. All right. This one is going to be, I'm going to leave it at a 0 offset because we're going to create the final feature of this. We're going to create the final feature of this using that tool that I made and then hid. All right. So anyone have a sense of what this is going to look like? Let's start lofting. So we're going to loft from here to here to here. I'm going to make sure to click along the path. Make sure you know which side you're clicking on so you don't do this and end up with a mess. So that's not what you want to do. So we have our loft. We need the final piece here. I'm just going to do a simple sketch at the end because we consume all the sketches and things, and we'll see what we're going to do with this tool here in just a second. So I've done this the way that I've done this, probably with some confusion, but for a reason. So I'm going to be lazy and do offset entities. Zero offset. And I'm going to extrude that for another 25 mils in the opposite direction, maybe 15. Just so that I have enough to get a real good clean cut on. All right. Now, that looks nothing like what we're drawing, sort of, kind of. There are a couple ways to deal with this, and this is what I wanted to show. So I'm trying to show broad general principles. Now let's bring back in this sketch. So I wanted to leave the profile alone here. I wanted to interfere with the profile down here at the back. And that's why I set this curve up the way that I did, because I want a center line. Becomes very, very important. And we're also going to need some connecting lines to give ourselves the effect of a die, a cutting die. There we go. Now we're going to trim off this tiny little end of the spline because reasons. Because I need this. I need this area definition to do the cut that I want to do. So one of the things that you can do is you can add fillets. Another thing that you can do is what's called a Revolve Cut. And this will make maybe a little more sense once you see it, because a fillet will look one way, a Revolve Cut will do something different entirely. So what I need to revolve is this around the center line. It automatically looks for those. I hit OK, and now you can see the geometry that I achieved using this. So this is a little different, a little bit different approach, and you'll see a different methodology that I use in Tuesday's video when I get that uploaded, possibly this afternoon. This gives you a way to change how these actually get cut. And so I wanted you to see what it looked like before versus after. So much of this geometry was altered slightly. Some of it was already down below that level where it didn't get affected. Some of it rose back up above that level again. So depending on how that's set, you can use the side profile to sketch or change what this value is. So if this comes down lower and you say, yeah, actually, it ducks down pretty sharply here. And then we have it's going to try and reconcile sort of all of those particulars. This is part of the reason why we don't spend a ton of time doing splines. They can be pretty tricky, and it kind of gets to a point where it's a little bit like working, trying to do serious work with a waterbed. And a waterbed is not exactly something known for its precision in operation. So this probably needs to be just a little bit higher, and we can change it to be a little bit more aggressive there and simplify the way that this tapers. It might even be a little bit more like that. All right, so this will change our geometry. There we go. So now we reselect that extrude cut. And the problem is with that depth, we now have smoothed out a lot more of our curves. But again, we have achieved a kind of scalloped geometry on part of it that we're looking for. So I'm trying to show you guys some of the different techniques and ways to approach this in terms of getting the kind of results that you're looking for, because it becomes fairly important to understand, hey, if I raise this up just a little bit and I don't duck down as sharply there, you might have a couple instances where you have some changes to the geometry. This might have to come back up. So you can play around with the splines and pull and tug at some of their different relationships and see how to make them tick. But you can often get something close to the result you're looking for. In this case, I don't want to be grabbing the tilt. I want to be repositioning the mechanism. There we go. So if we say OK, and we step out of the sketch, it now redoes that cut again. And depending on where it was positioned, how high, etc., what the offset is, it will change again. So you have these almost divots across the surface. So note to self, trying to recreate those particular kinds of geometries. This is how you do it. This is much more advanced in terms of technique and operation than what we've done previously. But I wanted to show you the capabilities of that Revolve Cut because it's going to behave very differently than simply coming in and trying to do a fillet across all these different edges. Because it'll sort of do things, but you really can't fillet faces very easily. And the radius of 10 really doesn't work for this. Even a radius of 3 kind of doesn't make sense because it doesn't understand what you're trying to go for. So even if you include those two edges, it's really, really hard to tell what's going on. Another thing that I'll see people do on this assignment is people will go, oh, I'll just do a fillet at the end. Ah, yes. I'll do it on all 4 corners. And then you get a geometry like this, which is really not close to what we have. And then you'll say, oh, well, maybe if I just do it a little more, that'll work. And then maybe if I do the same thing and I fill it again, maybe it'll get me closer. Maybe that needs to be a 2 or a something. You can get to a number of interesting geometry types, but you're still going to be limited in terms of your range of what you can do. So 2 millimeters is too much for that particular geometry to resolve. 1 millimeter is a bit much. So even still, 1 millimeter is a kind of a big problem. So you can try and get there with fillets, but the point is you're not really going to get there. At some point, you have to do a revolve cut to get some of the geometry that you're looking for. So I've got to get out of this tool so that I can make the adjustments to the spline that I need. There we go. There's a couple others. So this sketch is fairly easy to manipulate. You can do things a little bit more simply with arcs. So maybe you need a geometry a little bit more like that. And then you can do a Revolve Cut. So around that center line. And then you can see, instead of a fillet that's trying to change radius, you may have to do a Revolve Cut to get some of those kinds of features. Now, there's some other kinds of features that show up. And again, I'm not sure how else you would recreate this kind of almost pedal-like geometry outside of doing it this way. I suppose you could probably get close with fillet, but again, you're not going to get 100% of the way there. So this will get you close, but then what you're going to find is you've got a part at the end here, which is a circular sort of tail cap, and it has some cuts. So let's remind you what that looks like. So it has some cuts. So how do we recreate that with yet more reference planes? So now you guys have a sense of why it is that I have, no. You'll have a sense of why it is that I have all of the references that I do. So it needs to be parallel with this. It needs to have a second reference point. And a third reference point. I'm going to delete that face because that creates a point of confusion as opposed to a point. So part of the reason why I went with all of that particular spline edge and all the things was ultimately to be able to set up this plane referencing that point of intersection. So it's a lot of lead up and background for something that'll make sense in a second. So on that plane, you guessed it, we're going to need a sketch. And it'll be basically the best sketch there ever was. So we got to be careful about reference. But here, this is what we're going to do. We're going to keep the inside small. We're going to do a feature around the outside. I'm going to make a centerline reference. We're going to do a feature. And it's basically going to be like a toothed cut. We're going to add another circle and then a third circle. That was not origin centric. That'll create asymmetry, which is a technique for the very, 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 very advanced class. All right. So this covers most of what I'm looking for here. All right. So we need to mirror these bits. We don't want to mirror the arc. We want to mirror this about center line. Could have used the dividing plane, didn't have to have the center line, but I'm trying to show you for sake of completeness. And we're going to trim entities. Then we're going to pattern. So we're going to pattern. Totally randomly selected number, not as though I've done this once or twice before. Yeah, spacing looks close. This one's a slightly different diameter than the last one. That's more correct. All right. So then just have to go in, trim out all the little circles, all these segments. Which takes 150 years, but will produce the result that we need. So it'll become clear why the effort is what it is. So when you remove all of these, there sort of are some other ways that you can go about this. You can copy over in a pattern like the arc segment if you predefine it and then get pretty close, but then you have to do some pretty precise figuring and much maths. I don't know how much you guys love doing maths. So now we're going to do our cut. And this will be an extrude cut. And we're going to go up to in the case of up to next, it will go all the way up to this part of the geometry so that you can see. And because of some of the particulars and the outer dimensions, now you see how you can create a geometry that drawing by hand, you just really couldn't manage. So this is why in SolidWorks, you are limited to your own willingness to experiment, try, and practice, not necessarily anything else. So we're going to go back and edit that feature because we don't actually want to do up to next. We only want to do up to a vertex. That vertex will be that joint. So we cut the tail cap in a couple spaces with our geometry. Then we do the same thing up at the front. When we unhide this, because by now you guys probably forgot that we even still had this. And there's a couple things that we can do to change how this is oriented toward our part. So here again, I'm departing and deviating a little bit from our inspiration, only because I'm showing some different techniques than I did on Tuesday. So I want you guys to be able to use both resources. learn different things from each. Because repeating the exact same class the same way is not exactly the most entertaining. So we'll demo that technique that I was mentioning. We'll do one more sketch. Front face. Add a sketch. Change the view. First things first. Base circle. Actually, we should be able to get away with just the arc. So we need it to be a little bit larger because reasons. And then we need lines. Need lines. And an arc. You could use a center point arc here, and it would work. But to define it, you have to do some sort of fancy math, and then you've got to mirror some of the entities. So I'm going to demo the process. Delete arc2. Mirror about that plane. All right. And then, in essence, what we're doing here is doing the same idea. Linear sketch pattern. Circular geometry. 26 total copies of and this really needs to be just a little longer. So we can kind of sort of cheat. We could add another one, get ourselves closer and closer and closer. So right about 34, at least, should give us a point of intersection. And then we might be able to, you could also cut it short and edit that line length. And that's what we'll do here, is we'll cheat. So as a little magic trick, that one's free for today. That will give us our enclosed region. A couple of you probably just woke back up and thought, well, gee, I should have paid a little more careful attention. Selected contours. I'm going to select that whole region. Up to vertex. So I'm going to find an intersection point. So because of the depth and because of the selection there, actually just wanted the outer region. But in case you wanted to make psycho spikes of death, that's your method. So you can make a geometric cut through one of the parts, through part of it, and that's the methodology that you're going to use. So that pretty well covers the techniques that are involved. I'm going to set a material for this, and then we'll put it together as an assembly and see what that looks like. So the handle generally is going to be something like ABS. So ABS, we're going to save this as driver handle. Okay. And what we're going to do is create an assembly. Make an assembly from the part. When you start adding lots of complex lofts and geometries, this becomes much more RAM intensive. Probably your computer will slow down considerably. So I've already got the handle selected here. I'm going to add one more. So assemble, insert component, add the shank. Don't worry that it's in backwards. I could put it over here or wherever I want to. We'll learn a lot more details about assemblies later because I'm going to add mates and tell things how to be. So I want to pre-select concentric because I know where I'm headed. You'll learn why later. Concentric. And I'm going to flip orientation, do a little magic, do a little more magic, and do wireframe because I need to catch that edge. Wireframe. Concentric. I need not concentric, but coincident. This face and this face. Nope. There we go. That face, that edge. So this is what it would actually do and how it would actually sit in the real component. All right. Go back to display view. And we've put together our driver. Now that we have both materials decided, we can actually go to evaluate, look at our mass properties, 42 grams, very lightweight, but realistic and representative of what a real screwdriver would be, somewhere in the ballpark of 40 to 60 grams, depending on size, etc. All right. So that should all be clear as day, and you guys will all have beautiful, amazing, wonderful screwdrivers by the end of that assignment, right? So I'm going to pause it for a second. So I'll do one more quick part, but in order to demonstrate what's possible, I'm just going to focus on the part creation and not the teaching so much. That geometry is a little too easy. I'm going to do something a little more challenging. Let's see if it can resolve connecting. No, that geometry is going to be a little too savage to connect. Too many compound curves. That should have just enough character to resolve. However, the guide curve is going to be a little too tight because of some non-definition that's going to happen over here at this edge. eliminate this as an edge curve, redefine it as a center line. And there we are. Part. So a geometry you could not really get to any other way without spending many, many hours, done in a handful of minutes. So I don't actually know how many minutes that was, but not very many. So setting dimensions and things, if you know where you're going and what you're trying to accomplish, you can get there pretty quickly, even having to get a couple steps back. But every time you begin a sketch, you have to begin with the end in mind, which is a good general life rule. So, and that's under caffeinated on only a handful of hours of sleep for the week. So there's that. All right. Any other questions? I'll go ahead and pause it because the video is pretty much done here.